Hello everyone, this is Sneh Suman Purbia from group 316. Here is my topic structural instability. Definition: structural instability is a phenomena where a structure deforms a lot while the external forces increase by a small amount. The elastic stress analysis of the structure is based on the assumption that the applied force produced geometry sufficiently for effect associated with the change of geometry to be important. In many practices, a structure these assumptions are valid only up to a critical value of the external loading. Bucking. Bucking instability is a treacherous phenomena in structural engineering where a small increase in the load can lead to a sudden catastrophic failure. It is a sudden loss of stiffness at a critical load which results in deflection to a side. Uh, where instability occurs whenever a light or thin uh, when or then important component is subjected to comprehensive load, the possibility of bucking should be considered. It should be noted that a pure shear load on the plate or shell can be resolved on into a tensile and a comprehensive component, and so the structure might buckle under this load condition. In context of biomechanics, bucking is the most likely to occur in long, slender columns, long bones, in thin shells, in orbital floors. Euler theory. Work on a bucking of column was developed by Euler in the mid 1st century. Euler methods are attractive for the solution of simple column with a simple resident condition because the solution are closed form and accurate. So let's understand the Euler theory with the help of long bones. Consider a thin rod with a lateral deflection indicated by a broken lines. If the column is in the equilibrium, the bending moment is m at the distance of x along with the beam is uh, with the formula m is equal to py. By the engineering theory of bending, we know that the differentiation square of y upon dx square is equal to minus m upon ei, which is equal to minus py upon ei. Definition of variables says that the lambda 2 is equal to p upon ei, and rearranging we can say that the d square y upon dx square plus lambda square y is equal to 0. So this linear homogeneous second order differential equation has the standard solution, that is y is equal to c sin lambda x plus d cos lambda x. So, the constants C and D can be formed from the boundary condition at the end of the column. Substituting the boundary condition y is equal to 0 and x is equal to 0 gives d is equal to 0. The second boundary condition is the y is equal to 0 at x is equal to L gives c sin lambda L is equal to 0. The first and obvious solution to this equation is the c is equal to 0. This means that the lateral displacement is 0 at all points along the column, which is therefore perfectly straight. The second solution is that the sin lambda L is equal to 0, or by this equation lambda L is equal to n pi, where n is equal to 1 2 3 etc. For this solution, the constant C is intermediate, and this means that the magnitude of the lateral displacement of the column is uh, intermediate. At the value of the load that correspond to this solution, the column is just held in equilibrium with an arbitrary large or small displacement. The value of this critical load can be calculated by substituting the lambda. We having an equation that is the under root of PCR upon EI multiplied by L is equal to n pi, for which we can say that PCR is equal to n square pi square multiplied by EI upon L square. Although the magnitude of the displacement is unknown, the shape is known and is determined by the number of half sine waves over the length of the beam. The lower value of the critical load is that when n is equal to 1, PCR is equal to pi square into E into I upon L square, and this is well known formula for the critical load of a column. It is interesting to illustrate the result of this analysis graphically. You can see in this graph that P load is in the x-axis and y max, that is the peak lateral deflection, is in the y-axis. And you see the stable equilibrium is this and the unstable equilibrium is this, and this line indicate the natural equilibrium. Let's read. If the load is less than the critical load, then the only solution to the differential equation is the C is equal to 0, and the column is stable at a critical load. The two solutions become possible with either the column remains straight when C is equal to 0 and the critical can continue to increase, on the lateral displacement become intermediate, and no more load can be sustained. The first solution corresponds to the solution of the unstable equilibrium, and any perturbations, even one caused by the initial imperfection of the column, will cause collapse. Although this curve can modify using more sophisticated theories based on finite displacement, and it can be demonstrated that loads higher than the critical load can be sustained. The associated lateral displacement are high and designed in the region is normally impractical. The Euler in instably load represent a realistic upper bound to the load that the column can carry in compression. The graph can be redrawn with the axial deflection on the x-axis, and then it is apparent that there is a sudden change in the axial stiffness of the column at the critical load. Now let us read the another topic, that is the comprehensive failure of the long bones. It has been demonstrated that the stability of the uniform column is proportional to its flexural stiffness, that is we know that EI, and inversely proportional to the square of its length. It is likely, therefore, that the most vulnerable bone in the skeleton will be long bones in the leg, since the governing property of the cross section is the second movement of area. As for bending stiffness, it is apparent that the hollow cylindrical cross section might be most efficient in the resisting booking. You can see in this diagram, this is the length 1 meter. Here we can give the pressure. This is the cross section where we can see that there is an R radius and T is the thickness. The bucking strength of the non uniform column will always be higher than that of the uniform column of its minimum density. The bucking stress is simply the bucking load, which is divided by a cross section area. Here we have a formula, PCR is equal to pi square EI upon L square, and sigma CR is equal to pi square EI upon AL square. The bucking stress can be calculated and compared with the ultimate compression stress to determine whether the failure will be bucking on it by simple overloading. In either case of the result will be the same, a broken leg, but the appearance of the fracture might be different, and the design step required to prevent the recurrence will certain be so. Okay, so this is my video. Thank you for today.